Most failures in RAG systems are originated in the pipeline, specifically due to how context is retrieved and selected. In today's video, we will focus on advanced techniques in retrieval process. The goal is to understand how production-grade RAG systems decide which context is worth showing to the model, and how better retrieval decisions lead to more reliable responses. Welcome back to the channel. This video focuses on a single question that determines whether a RAG system succeeds or fails. The question is, how do we choose the right context? Before we go deeper, let me briefly outline what we covered in the previous video. In the previous video, we built a basic RAG pipeline from ground up. We looked at how chunking, embeddings, and vector databases work together to retrieve relevant pieces of information and provide better context to LLM. The idea was simple. Instead of just relying on models training data alone, we allowed it to reason over our internal documents at runtime. But as we saw, even with retrieval in place, RAG systems can still hallucinate or produce incomplete and incorrect answers. So, by end of this video, you should have a clearer understanding of how advanced retrieval techniques like re-ranking, hybrid search, and filtering improve RAG systems, not by changing the model, but by generating better context for it to reason over. We look at dense versus sparse retrieval, why hybrid search is used in production systems, re-ranking using encoders and LLMs, and metadata filtering as pre-retrieval control. I'll also demonstrate how these techniques change outputs using the same model and the same dataset. With that scope in mind, let's start by examining why a basic RAG pipeline is often insufficient in real-world systems. Typical basic RAG pipeline is straightforward. Documents are split into chunks. Each chunk is embedded. A vector database retrieves the top k chunks, and these chunks are passed directly to the LLM. This design optimizes for simplicity, but this is not reliable because there are limitations to it. First limitation is that the similarity is not always equal to answer relevance. Embedding similarity answers the question that which chunks are semantically close to the query. It doesn't answer that which chunks actually contain the information required to answer the question correctly. This distinction usually matters when multiple documents discuss the same concept, and only one contains the precise constraint or response that the user expects from LLM. The second limitation is noise accumulation. Large language models do not evaluate each chunk independently. They attend over the full context window. As you add weakly relevant or generic chunks, the attention is diluted and important details are overshadowed. And also the model begins to interpolate and speculate. This is why adding more context often makes answer worse than better. So when basic RAG starts to struggle, the natural next step is to look at the retrieval. In practice, there are two very different ways retrieval systems work, and they behave quite differently. So we look at those two approaches, which are dense retrieval and sparse retrieval. So let's look at the dense retrieval first. Dense retrieval uses embeddings to capture semantic meaning. It works well when queries are phrased differently than the source text. The answer is conceptual rather than exact. For example, if the query is, how does cross-account access work in S3? Dense retrieval works well in this case because the keywords like cross-account, S3, access may be phrased differently across documents. So semantic similarity matters. Next is sparse retrieval. Sparse retrieval uses keyword matching for exact term frequency. It performs best when exact terms matter, and the queries include identifiers, versions, or error messages. For example, if the query is access denied, STS assume role is not authorized, sparse retrieval outperforms embeddings here because exact string match matters more than semantic similarity for the error messages. In isolation, each approach has clear strengths and equally clear blind spots. In production system, relying on only one of them is rarely sufficient. This is where hybrid search becomes relevant. Let's look at hybrid search. Hybrid search combines dense and sparse retrievals to improve recall. The goal here is not perfect ranking, it's ensuring the right information is at least present in the candidate set. exact term matching and understanding meaning, leading to more relevant results for complex queries. A standard hybrid retrieval flow looks like this. Run embedding search and return 20 to 40 chunks. Then run keyword search and also return top 20 to 40 chunks. Merge them and deduplicate the results. At this stage, we still do not assume the ordering is correct, but it's the best of both. The goal of hybrid search is not ranking accuracy, it's recall. In hybrid search, the recall is the metrics that measure the completeness of the search results, the percentage of all truly relevant items within a database that the system successfully retrieves. However, after hybrid search, we expanded the recall and we introduced a new problem. We now have more candidates, but not necessarily better ordering. That leads directly to the need for re-ranking. Retrieval systems are optimized for speed and coverage. Re-ranking is the layer where precision is introduced. Ranking in RAG systems refer to the crucial post-retrieval step of re-ranking, where an initial set of retrieved documents is reordered by relevance to the query, ensuring the most important information is sent to the LLM for more accurate and contextually appropriate answers. This tackles the noise from initial retrieval by using more sophisticated models like cross-encoders to deeply understand query document semantics, elevate decent retrievers into high-quality RAG systems. Ranker selects the top 3 to 5 chunks to improve the consistency and reduce hallucinations. Another technique is metadata filtering. Even with strong re-ranking, there is still one important optimization that happens just before retrieval even begins. That's through the metadata filtering. Metadata filtering limits what is eligible for retrieval before scoring begins. Typical filters include things like document type, product or service, version, date range, environment. This reduces noise before similarity is even calculated. Now that we have covered the core concepts, let's see how these decisions affect the real outputs. We'll do that by walking through a concrete demo using the same dataset and same model. Now I'm going to run a small Python demo to illustrate how basic retrieval fails in practice and what changes in the pipeline when we add advanced retrieval techniques that we just discussed. So first, let's quickly understand the dataset. I have 5 documents inside. Each document has some metadata like a document ID, title, service, and then the actual text. In real system, this metadata is critical because this is what allows us to restrict the retrieval to the right domain or the right version or the right time range. For example, here we have S3 cross-account access document, which is the best source for this question, the question that we are going to ask. Then there is an IAM versus resource policies, which is a bit relevant, but it's very generic, not answer specific. We also have S3 policy example document, which is deprecated, and a Terraform config Terraform S3 module node, which is implementation related. And there are a few more documents like S3 overview, which is high level and generic. In real projects, you will have thousands of documents like this, and the retrieval needs to pick consistently the right ones, so the metadata really helps. The next section is chunking. We are chunking based on the paragraph. We are labeling it as a document ID. For example, if we are picking it up, it's D5P1. Now let's go to the main function and run the basic RAG pipeline. So the basic RAG pipeline is, this includes dense retrieval only, which is extracting the top 5 chunks, then vector similarity, no metadata filtering, and no re-ranking. So let's run this function. Okay, let's understand the output. So the first line is the chunk ID and the score. Score is how relevant the retriever thinks this chunk is to the query. In the basic RAG that we just ran, it's the dense similarity, which is how semantically close this answer is to the query. But when we run the advanced RAG, the score is your re-ranker score, that is combination of hybrid search and everything else. So here we can see that it has retrieved 5 chunks. The first one says The first one is S3 cross account access recommended, the first paragraph, which is good. The second one is a generic IAM statement, which says cross account access typically requires granting the principal permissions to call relevant actions, which is a general statement. The third one is S3 cross account access recommended, which is common required S3 permission depend on the use case, which is good. Then the implementation details, which we did not ask for in Terraform. The fifth one is for cross account patterns, bucket policies are commonly used, which is a very generic statement and not relevant in this case. So the key observation here is that it did not bring the most operationally useful chunk, which included the policy permissions like S3 get request, get object, S3 list bucket, S3 put object. It just returned very generic and high level chunks, and that's the reason of a lot of noise. So as mentioned before, dense similarity is good at finding text that is topically related, but it's not guaranteed to return the chunks that actually contain the precise answer. So typically what happens is it retrieves intros, summaries, wherever it finds the similar text, but the paragraphs containing the precise requirement like S3 actions, trust policies, assume roles, etc. are not always ranked in the top results. That's the core reason why sometimes RAG struggles, and it retrieves related context, not necessarily answer bearing context. Okay, let's move to the advanced pipeline. I'm going to comment the basic pipeline code here, and we are going to run the advanced pipeline. What we are going to do here is we are going to run the same query, but this time through the advanced RAG pipeline, where we are doing hybrid search, metadata filtering, and re-ranking. Then let's go to this function and see what we are going. So first we are retrieving candidates via dense and sparse, which is hybrid search. So dense retrieval is best for meaning and paraphrasing, as we discussed just in the basic pipeline, and the sparse retrieval is best for exact terms like service name, error messages, or S3 policies in our case. Hybrid search includes and improves the recall by collecting candidates from both sparse and dense and then deduplicating them. That's what we are doing in the first part. Then we are doing metadata filtering in this section here. So before re-ranking, we filter out chunks that we should not be considered. For example, we are only retrieving the keywords where the service is S3. The document type includes guide or config, and the doc type exclude deprecated content. Then we move to the next section, which is re-ranking. Initial retrieval, which is hybrid search, is optimized for speed and recall, but re-ranking is where we optimize for precision. Here we take the candidate set, which is filtered, and we score each chunk based on the lexical overlap, presence of critical terms, and we add penalties for unsafe or deprecated patterns, and we add small bonuses based on metadata. And in production, you would often use a cross encoder or an LLM for this step, and score the chunks based on whether they answer the query or not. And let's run the advanced RAG pipeline and look at the difference. So let's understand the output again. It's again the scoring, which is in this case is re-ranker score. The first one is S3 cross account recommended, which is the best solution out of those 5. So this is good. Second one is from the recommended answer again, which is the policy. It's the key improvement we can see here. It's now returning the policies detail. The third one is S3 put object, then get object, and then the cross account variant. But you can see the real improvement in this answer. And the context derived says that it includes all the S3 policies that we need and the more specific details to the answer. So we can see that it's returning more action level chunks than the basic pipeline did not include. To wrap this up, the main takeaway from this video is that RAG quality is determined far earlier than generation. By adding hybrid retrieval, metadata filtering, and re-ranking, we shift the system from related context to answer-bearing context. And that's the main difference between a basic and advanced RAG pipeline. If you like the video, subscribe for the next part of the series, and I'll see you in the next part.